All right, good evening, everyone. Who wants to start us off with some questions? Anyone? Questions? Bueller? Bueller? Can you all hear me?
Yep, I can hear you. It's Christina. I don't want to monopolize all the questions. I always seem to do that. I'm trying to be.
Well, it doesn't seem like anybody else wants to ask anything, so go ahead.
The only one that I was a little bit, I kind of alluded to this, and I think I was getting this confused as I was looking ahead on the week 5 homework, but can you just explain a little bit around when, and I know for this homework we were doing, probabilities using a binomial, but can you explain a little bit again about like when you go one less than the X value and when more? Because I just feel like I know jumping into week 5, like that just got me a little bit confused.
Yeah, totally. So the problem with the whole binomial normal approximation thing is that, the binomial is discrete and the normal is continuous. So, if we have a binomial that's set up, let's say 1, 2, 3, 4, 5, 6, 7, right? We've got these bars. The problem is that each bar is going to be centered on the number, and there's gaps. So that's not perfectly normal, but you get the idea. If we want to now approximate it with a normal curve, and they say, they want, for instance, let's do we'll do it. The probability that X is less than or equal to 4. Well, for the binomial, right, if we were going to do this precisely with the binomial, we would literally just take this, 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 and then of course the one for 0. And that's the probability of being less than or equal to, less than or equal to 4. So we want this one as well, less than or equal to 4. And that would give us the precise answer for the binomial. But we could approximate it by finding the area under the normal curve. But because this thing is centered, right, the center line is sitting right on 4. So when they start talking about, less than or equal to 4, if we then came along and did the probability that X is less than or equal to 4 for a normal curve, it's going to do all of this. And can you see that it misses half of the bar for 4, right? Because when we do normal probabilities, it finds the area under a curve in between two things, or less than something or greater than something. So in this case, less than 4 or greater than 4. And I've talked about this before, less than 4, unless this is actually, if you didn't know this equals the probability that X is less than 4, because the probability that X equals 4 is 0, because there's no area, right? To find area under the normal curve, you have to have a width. And if you say X is equal to 4, not equal to 0, equal to 4, it's just this thin little line above 4, and it's got no width, so it's got no area. So these two things mean the exact same thing. So when we're finding the area under the normal curve with 4, it's going to cut off half of our bar, right? Half of our bar that represents the probability of it equaling 4 in the binomial. So in order to get a more accurate estimate when using the normal curve, we have to take it up to 4.5 to capture that last half of the bar. Now, technically I should have drawn these bars touching, right? Because 4.5 would be right in between 4 and 5, but I kind of over exaggerated. So we can look at another one. Another example. Come on, where are you? There you go.
Are you saying anything, Dr. McBride? Because I don't hear you.
No, I'm just drawing right now.
Okay.
I can't talk and draw. I'm too stupid.
My computer's raggedy, so I thought it was me.
All right, so let's say this is our new binomial distribution. Again, each bar is always centered on the number. And then if we, try and fit a normal curve to it, it'll look something like that. And so now let's say we want to find, again, with binomial, we want to find the probability that X is strictly greater than, let's say, 8. Well, strictly greater than 8 is just all of these bars, right? Everything bigger than 8. So if we try and approximate that with the normal curve, and we go, okay, so let's take the probability that X is greater than 8 with the normal curve. Well, greater than 8 comes right here. That's where 8 is, right? Remember, 8's right in the middle of the curve and gives us everything to that side. And now you'll notice that we have this extra bit here. We basically have half of the 8 column that we don't need. So a better approximation would be the probability that X is greater than 8.5, because then that would cut us off right here, because this line, right? Maybe I should do it in a different color so we can see, and this be red. 8.5 would be right here. And then we would get a more accurate estimate. So that's the continuity correction, or correction for continuity. It's called different things in different sources, but you're correcting the error that happens when you're going from a discrete probability distribution, the binomial, to a continuous probability distribution, the normal curve. And so in order to get a more accurate estimate, you have to bump it either up or down a fifth, depending on which direction you're looking for. So if you're trying to find the area, or you're doing the probability of something less than or equal to, then yes, you will always bump the normal up by a half. Just like if you're looking at greater than or equal to, you'll always bump it up by a half, right? So it seems like everything always goes up by a half. Well, I always say just draw a picture and you can always figure it out that way. So the last example I'll do is if you wanted to find, and I'm just going to do a simple one because I don't want to spend an hour drawing these things again. Right, you want to find the, so this is 0, 1, 2, 3, 4, 5, and 6. Let's say you wanted to find, again, with a binomial. So binomial, oh, no, All right, should be consistent. The binomial, the probability that 2 is less than x is less than 6. Right, so if x is between 2 and 6, we only want 3, 4, and 5, right? Because we're strictly in between 6 and 2, and for a binomial, you know, you can't be 2 point something. It's either 2 or it's 3 or it's 4 or it's 5, right? It's discrete. So if x is greater than 2, it starts with 3. If it's less than 6, it ends at 5. So we really only want the area of those 3 rectangles. Again, if we fit a normal curve to it, and then we come in here and we go, okay, so for the normal curve, if we do the probability between 2 and 6, it's going to cut here and here. And that's no good, right? It gives us half of 6 and half of 2. It gives us half of the area of the binomial rectangle that represents 6, and half, it gives us too much, right? So instead, we do the correction for continuity, and we go, all right, well, according to my picture, if I do 2.5 and down to, right, so I want to stop here and here, so that's 2.5 in between 2 and 3, and that's obviously 5.5 because that's between 5 and 6. That's going to give me a more accurate estimate in my normal curve. So I tell students, don't try and memorize, do I always add a half? Do I always subtract a half? Just draw a quick picture and figure it out that way. Because yes, there are rules for when you add and when you subtract, but it's not worth wasting your brain power trying to remember them. I don't have them memorized. I draw a picture each time and go, oh, that's right, I add here and I subtract here, right? That kind of thing. So that's the correction for continuity theorem, or whatever. That's the rule. That's how we do it. Does that make sense?
Yeah, and I think honestly the challenge for me is like when I'm reading the problems, I know whether I'm supposed to use the binomial function in SAS or the normal function. Like I know, the questions pretty much tell you when you should be.
Yeah.
I just couldn't remember like with the normal distribution function if you needed to make that adjustment. But then after we exchanged emails, like I read a little bit more about like discrete versus continuous distributions, and then it kind of made sense because it's an area under the curve issue. So then it made sense to me, but I thought I did all the problems wrong is what I thought I did wrong.
Yeah, no, it's exactly that. You just have to make small adjustments when you're switching from that discrete to that continuous, because like you said, the area under the curve gets to be a problem. It's kind of a silly thing. I don't know. I honestly don't know why we still teach this. I've really been racking my brain for the last 5 years, asking myself, is there really any learning advantage to this whole idea of approximating the binomial with the normal, right? Do students actually learn anything seeing how a continuous curve relates to a discrete curve, and how the areas are similar yet different? I'm struggling with how that helps with the learning and understanding of the concept of a normal curve. Because really it all boils down to, in statistics, we really need to understand how the binomial curve looks and works, because we do a lot of work with binomial data. So it's good for students to understand how binomials are created, what the properties of a binomial is, that there's a finite number of outcomes, that each of them is independent, each of them has a set probability and that doesn't change, and the probability of success is always the same. All those kind of properties are important to understand how to fit something to a binomial, so then you can calculate something using a binomial. But then the more important thing is the normal curve, because all of statistics, everything you do in statistics, whether it's a hypothesis test or a confidence interval, all of those things are built on top of the concept of what a normal curve is, the properties of a normal curve, and how you find probabilities underneath a normal curve, i.e. by finding the area in between two values. I don't see how understanding both of those concepts is in any way, shape, or form enhanced or made better or easier by doing this whole idea of approximating the binomial using the normal. It baffles me. I can't figure out how it's beneficial. I really think that it's just one of those holdover things that we've been doing for so long and we're still doing it. And the only reason why we did it a long time ago was because without the advent of computers and technology, you could not calculate large binomials by hand easily, but you could always calculate, no matter how large something got, area under a normal curve very easily because it was a simple integral you could do in calculus. And so way back when, before we had calculators and we could calculate binomial probabilities, between two numbers when we're talking about big things. So not something as small as this where you only have 6 trials or 14 trials. Talking about something where you've got 500 trials and you want to know what's the probability that you get, less than 300 successes out of 500. That would be friggin' impossible to do by hand. I mean, it's not impossible, but it would take a crap ton of time to do it by hand. Whereas you could then fit a normal curve to it and approximate it pretty damn accurately with a normal curve, and you could do that one by hand very easily. So I think it was a technique that was bought out of desperation, decades ago before we had fancy calculators. And now that we have them, I really don't see why would you ever approximate something when you can actually now compute the precise answer very easily. So that's my quandary. I still don't understand why we're teaching this, but c'est la vie, there it is.
So along those lines, can I ask a question about the when will we use inferential statistics around random sampling distributions? Is that just practically speaking, I totally understand why we use it, if you're looking at a sample of data, right? You're looking at distribution analysis, but when you're looking, is that so that you can make sure that your random sample is reflecting the population of interest? When will we use that?
Actually, it all comes down to the idea that, so we know that if we sample, and it doesn't matter what our population looks like, our population data could be normal, it could be skewed, it could be bimodal, it could be uniform, it could be any shape we want. Doesn't matter what our population of data looks like. If we took every possible sample of size 20 or bigger from that population, and then calculated a statistic from that sample, and we could do it with means, medians, proportions, if we have proportion data where we really don't have numbers, we just have yeses and nos, and you can count up how many yeses and how many nos, so that's proportion, that kind of thing. So if you have qualitative data, you can still do proportional analysis. So means, medians, proportions, those are the 3 biggies. It also works with standard deviations and other measurements, but it gets a little trickier. But if we just think about the mean, because everybody understands the mean. So you have a population of data. It doesn't matter what the shape of your population is, right? Your population could have, it could be uniform, where everything has equal probability. It could be hugely skewed, right? It could be bimodal. It could be, just some weird shape. Whatever it is, doesn't matter what your population looks like. If you took every single different sample of size 20 or larger, and you have to go 20 or larger, otherwise the central limit theorem doesn't work. When they're smaller, the shape just doesn't come out to be perfectly normal. But as long as your samples are 20 or larger, they tend to be perfectly normal. Some books say 30 or larger, some books say 40 or larger. There really hasn't been any large statistical analyses to determine what that cutoff is. but it seems to get normal enough at 20 or bigger. If you're 40 or bigger, then you know for sure it's going to work. But so anyways, so let's say we have a population that's all weird, and we go and we take every single possible sample of size, let's just say 40 to be safe, from that population. And from each of those samples of 40, and there's going to be literally hundreds of thousands of samples of size 40, depending on how big your population is. And every single one of those samples, you calculate the mean, and then you write that number down. And then you go grab the other sample of 40, you calculate that mean, you write it down. So now you have hundreds of thousands of pieces of data that all represent the mean of each sample. Now that group of data becomes a new set of data, right? You now have a set of, let's say, 300,000 data points that are all means that came from these samples from the population. Well, that's called a sample distribution. You now have a distribution of sample means. And if you took those 300,000 data values and you plotted them, you created a frequency histogram, right? So you have little bars for heights showing how often each number showed up. If you create a frequency histogram, it would be a perfect normal curve. And so what that tells us is that, and more precisely, the middle of the normal curve is always the mean, right? This is X bar. If you're talking about samples, it's mu. If you're talking about population. But the middle of your sampling distribution is always going to be the exact same thing as your population. So basically the average of all of your averages will be the average of the population. That's just how averages work. And we also know that the standard deviation of our sample distribution is always going to be the standard deviation of our population divided by the square root of our sample size. So in this case, if we were taking sample size 40, it would be the sample standard deviation divided by the square root of 40. So that's kind of cool. So we know the mean and the standard deviation of our population. If we were able to take every single possible sample of size 40, well, that's not possible. We could only do that if we actually had the entire population of data. And if we had the entire population of data, why would we do all this crap when we could just take the mean of that population and the standard deviation of the population, right? So, but the idea is we know that in theory this works. So now if you have one sample of size 40 and you calculate the mean of your one sample of size 40, you know it has to land somewhere in this distribution. And we know that based on how the normal curve works, we know that 68% of all results are within one standard deviation, right? If we go plus one standard deviation and minus one standard deviation, that's 68%. We know that if we go out 2 standard deviations in both directions, that's 95% of our data. And if we go 3, then that's going to be 99.7% of our data. Well, we can calculate those widths, right? We can calculate the standard deviation of our sample, right? Because this is also the same thing as standard deviation of our sample, right? The standard deviation of our sample. So this distance, each one of these distances is our standard deviation. So let's say we, our mean is, let's say 100, and let's say our standard deviation of our sample is 5. Well, then we know that if we have, this as a 5, we know that if we go out 2 standard deviations in both directions, I'm going to put it back in the right color, that we've basically gone, right, plus and minus 10. We've gone up 10 and down 10 because our standard deviation is a 5. So we have what's called a confidence interval. We have a 95% confidence interval that has a width of 20, 10 in this direction, 10 in that direction. So now that tells us that 95% of every possible sample mean will be within this plus and minus 10 of the true population mean, which we don't know, right? So we don't know this in real life, but we know that if we have our sample mean, and then we build a confidence interval around it. So we take this sample mean, let's say our sample mean is, 92, and then we add 10 to it. So we go to 102, and we subtract 10 from it. So we go to 82. We can say that we're 95% confident that this interval captures the population mean. That the population mean should be somewhere between 82 and 102. And in fact, it was 100. So it did land in here. Well, I made all this crap up, but the idea is we can be 95% sure that this happens because we know that 95% of our values, our means from our samples, have to be within this interval. They have to be between, in the case of this, 110 and 90, right? Because this is what it would be if we centered it on our population mean of 100 and we want 10 and 10. So it's kind of like knowing that that's the chances that our mean is in here. It's kind of like a probability that's saying that there's a 95% chance that when we pick our sample, it's one of the samples that creates a mean that is somewhere in this range. So confidence intervals come from this idea of the normal curve and knowing how area works under the normal curve. And so do hypothesis tests. Hypothesis tests come from this idea, because the whole idea is this is what we assume to be true, right? When we have a hypothesis test, so it's the same idea. With a hypothesis test, we say, all right, the null hypothesis says that our mean, our normal curve is centered right here. This is our null hypothesis that, the average is equal to, 35. So this is sitting on 35 on the number line. And then we go and say, okay, our alternative hypothesis, our H1, is going to be that that the mean is actually greater than 35. We think that the mean is actually greater than 35. So then we go out and we take our sample and we calculate the mean of our sample. And it turns out that the mean of our sample is right here. And it's, let's say 40. And so based on assuming that this is where it should be, we can then calculate the area under that curve and say, all right, if the world worked this way, if our population mean was in fact 35, then we know this would be the curve that would represent all possible samples of size, whatever our sample was. Again, we'll say our sample was, let's say this time it was 30 instead of 40, right? So if all possible samples of size 30 would create a normal curve like this, it'd be centered on 35 because that's the population mean. And then we could calculate the standard deviation, all that crap. And then based on that, we could then find the area under the curve greater than 40. And that area ends up being, let's say, 15%. Right, 0.15, so not 0.15%, 15% or 0.15. So that means the probability of getting a sample that's greater than 40 is actually 15% or 0.15. Well, that's pretty likely. So we wouldn't reject the null. Normally, we want the probability of this happening to be less than 5% is what they're normally set at. But you can set it at other things. And the idea is if it is really small, if the likelihood, so instead, let's say our average was, way out here at 55. And when we calculate the area for 55, so let's put this in a different color. And we do the area for 55, and this comes out to be 1%. Well, then we have to realize one of two things happen. Either the population does in fact have an average of 35, and we just happen to win the lottery and get that 1% possible sample that has a mean of 55. It's not impossible. There's a 1% chance it could happen. So it's absolutely possible that it could happen, but it's also very, very unlikely, right? It's only a 1% chance. What is more likely is that the mean of our population isn't actually 35, that it's bigger than 35. Maybe it's somewhere over here. Maybe it's somewhere over here. But if it's in either of these places, then your curve looks more like that. And then when you calculate the area under that curve, you get, something like 15, 20, 25%, and that's more likely, right? So it's far more likely that it sits on a curve that's actually shifted further to the right. And that enables us to say, you know what, I'm going to reject this null hypothesis in favor of the alternative, because my sample is so rare on that null hypothesis normal curve that it's probably more likely that the curve is actually centered somewhere else. And again, all that comes from understanding what it means to find area under a normal curve. So the two big thing in inferential statistics that we deal with is confidence intervals and hypothesis testing. And neither of those two things can exist without the central limit theorem and finding area under a normal curve. And that's really everything we're going to learn next week. Does that kind of explain why we deal with this stuff a bit?
Yep, very helpful.
Awesome.
Yeah, it's pretty helpful because we were dealing with some stuff like this in a research project we're doing as a school district today, the high school principals, and we were just talking about the different variables and just this whole thing just makes more sense.
Good. Do we have any specific homework questions or final project questions or anything you guys want to go over tonight?
I have a question on 416B and C. I think I was just not thinking correctly. So is it supposed to be the same thing as what is the probability that a white donor, so given that it's a white donor, but they do not have blood type A, they can have any other blood type.
Right. Yes. So question B is a conditional or a given condition, right? So it's basically the probability that they don't have type A given that they're white. And then the same thing with part C, you're looking for the probability that they have type A or type B given that they're Asian, right? So both of those, B and C, are in fact given conditions. They are conditional probability questions. You're not just looking for the intersection of being white and having type A, right? So 32.2 is not the answer for part B. You have to calculate how many type A blood, what's the probability of having type A blood given that you already know that you're white, right? So it's going to be 32.2 out of that whole set. So for instance, if we look at these numbers.
Or is it opposite? It's because it's will not
sorry,
have
you're
a
right.
type.
Sorry, you're right. They asked for not type A. My bad. I keep forgetting it's not type A, right? So if we were going to do this one, B, and it says, so it's the same question. I just put different numbers in here, right? So they can't have type A, but they have to be white. So we're looking for this one, and this one. So that's going to be my good, right? So my probability is always good over total. So in this case, it's going to be 30 plus 10 plus 3. And then my total is, because I'm given that they're white, it's just all of this is my total. So that's going to be, 30 plus 25 plus 10 plus 3. And we get an answer of, what was that, 43 over 68. And then we would, stick that in our calculator and get a decimal, and that would be the answer, because it's a given condition, right?
Mhm.
Just like if we wanted to do this one. So they have to be A or B, but they're given that we're Asian. So we're only dealing with Asians. So we already know that our total is just 3, 4, 5, 6, 6.5. And out of those 6.5, how many good do we have? Well, it's the A or the B. So there's 3 over 6.5. And that would be the answer for C. So those are given conditions, right? If we wanted to do the simple ones, right? Being Asian and type O, that's easy. That's just 3 out of all of these numbers put together. And I think if I did this right, I think they all add up to 100. So it would just be 3%. And then of course, for D, what's the probability the donor will have neither type A nor type B, or sorry, AB. So we don't want A, we don't want AB. So we basically want all of these and all of these. You would just add all of those up, right? And it'd be that over the total, which again, I think is 100. So, you know, either the ors and the ands, those questions are really easy because and is just an intersection, or is just add all the crap together. It's when they become given conditions that you have to be a little bit, you know, you have to take a little bit step back and kind of think about it for a second, go, wait a minute, given condition is still really easy. It's just the given part creates a new subset, and that new subset is my actual total instead of the whole set being my total. And that's really all the changes.
Okay, got it. I think being the first question, it's just like I wasn't thinking.
Sure.
And then I have one more question about 21D, 421D. So I know these are not mutually exclusive. And how do I prove that in the probability? Like,
So if two things were mutually exclusive, that would mean the probability of one and the other would have to be 0. So you could calculate the probability of being white and having, what is T1, type O blood. And if it doesn't equal 0, then they're not mutually exclusive.
okay, got it.
And then the same thing for part C, more or less, when they talk about things being independent or not. If two events are independent, then the probability of either of the events happening has to be exactly the same probability as it happening, given that the other one has happened. So basically, you need to calculate the probability of having type O blood, and then calculate the probability of having type O blood, given that you're white. And if those two things are the same, if those two probabilities are the same, then they're independent. If they are not, then they are not independent. That's how you would prove part C. That's how you would justify your answer.
Got it. Yeah, I was able to think about that one, but not D. I wasn't sure. Like,
Yeah. Okay, anything else?
so I don't know if anyone else has any question. I have a question about the topic I critique. So they use the beta value. So I don't even know, like, so when we start working on this statistics, when we start writing our dissertation and we take the sample and do all this, how do we know what to use? Like, different studies are using different, some are using chi-square, some are using some other thing. So how do we know which one to use at that point?
Well, it all comes down to what kind of data you have and what kind of question you're trying to answer.
Okay.
I mean, really, that's what it all boils down to. I have a video on my website that talks about the different types of statistical tests and when to use each, right? And basically, it all kind of boils down to a couple families. You know, all these analyses, I group them into families. So first, it comes down to what kind of data you have. If you have, you know, regular old ratio level data, and ratio level data is the normal stuff. It's, you know, it could be discrete, or it could be continuous. But it's just the normal kind of data that we think about, things that we can calculate means and medians and standard deviations and all that kind of stuff. So if you have normal kind of numerical data, ratio level data, then there are certain analyses you can do on it depending on if it's discrete or continuous. And then if you're over here and you have, you know, nominal, ordinal, yeah, pretty much that. I mean, you're not going to have interval. Nobody has interval level data. So you have nominal or ordinal level data, which, you know, nominal level data are just, you know, names, they're characteristics. And then if you have ordinal level data, that's usually Likert scale or ordinal level data. Well, there are only certain kind of things that you can do with these. So when you have this type of data, really the only kind of analyses you can do are frequency counts. Because all you can do is calculate, well, how many things do I have with this name? How many things do I have with that name? So when I talk about nominal level data, it could be stuff like, you know, gender. How many females do I have? How many males do I have, right? How many people said yes to a question? How many people said no to a question? That kind of thing. And then with Likert scale data, it's really the same thing. You can really technically, and here's where everybody screws this up in the real world, with ordinal level data, you can still only do frequency counts. How many, so, you know, you guys have seen Likert scales. It's where it's either numbers, you know, from 1 to 5, or they have words that represent strongly disagree, disagree, neutral, agree, strongly agree, right? That would still be the same thing as a Likert scale from 1 to 5. There's an order to them, right? We know that agree is bigger than neutral and it's less than strongly agree, but there's no quantifiable, measurable difference between the two. So there's only an order to them, but there's not a measure to them. So that's why it's ordinal level data only. And technically with those things, all you can still do are frequency counts. You could say, okay, how many people agreed? How many people strongly agreed? How many people were neutral, et cetera, et cetera, et cetera. What happens is a lot of people treat this like ratio level data, and they calculate means and medians and standard deviations and all that crap. Because if you take your, you know, your Likert scale and you give them the numbers 1, 2, 3, 4, 5, then of course now you've got numbers instead of strongly disagree. You know, instead of having all these words, you have numbers. And people are like, oh, I got numbers, great, I can do numerical things with it. No, you can't, god damn it, because it's not. 4 is not twice as big as 2. And if you don't have that kind of relationship, you don't have that ratio level, then means, medians, and modes mean nothing. It doesn't, it fails. People still do it. And I'm sure if you had Likert scale data, probably some idiots on your dissertation committee would go, well, why don't you go ahead and run some summary statistics on those things? Just roll your eyes and do it because everybody else does, and just pisses me off. But anyhow, so if you've got ratio level data and you want to look at means, right? Then you're going to do t-tests. You're going to do ANOVAs. And those are the two biggies. T-test is when you have 2 groups. So you're comparing, you know, like the average of one classroom of students to the average of another classroom of students. ANOVAs is when you have 3 or more, 3+ groups. And again, it compares the means of 3 or more groups. So now you've got 3 different classrooms that all took a test, and you want to compare the average test score from, you know, each of those groups. Then that would be an ANOVA. And you can have 1-way ANOVAs and 2-way ANOVAs. And again, that's just more complicated we need to talk about. But those are the types of tests that you would basically do on this kind of data. And then, of course, you could do hypothesis tests. And then if you had, you know, bivariate data, i.e. things that are measured twice, then you can do correlation and regression, all that kind of stuff. Now over here with this kind of data, again, all you can do is frequency counts. So really the only kind of analysis you can do with frequency counts is, well, you can still do t-tests because you can test, instead of between means, you can do t-tests on proportions, right? So group A, 30% said yes. Group B, 35% said yes. And so now you can do a t-test to compare those 2 proportions and see if they are statistically significantly different based on the sample sizes, right? And then of course you can do hypothesis tests for those as well. If you wanted to then, so that's for 2 samples, right? So you've got 2 samples, you do t-tests. If you have 3 or more groups, well, you do ANOVAs over here. If you have 3 or more groups over here, you got to do a chi-square. So a chi-square compares frequency counts across 3 or more groups, just like ANOVAs compare means across 3 or more groups. So that's the big difference between what a chi-square does and an ANOVA does. An ANOVA basically compares 3 groups if you can measure something on them. Chi-squares compares 3 groups if you're only counting something, right? You're doing frequency counts. And those are kind of the biggies. And then of course, there's 2 different types of chi-squares. There's a goodness of fit and a contingency table, which is kind of the same thing as doing a one-way ANOVA versus a two-way ANOVA, right? So you kind of have these parallels between, it just depends on what kind of data you have, right? If you just have frequency counts because you have, you know, what I call shitty data, then you are stuck with chi-squares. But if you have good data, ratio level data, then you can do ANOVAs. And I shouldn't say shitty data because there's nothing wrong with Likert scale data and, you know, nominal level data. It's just, it's not real data. You can't do real things with it other than do frequency counts. But, you know, there's a lot of things in this world that you can only gather Likert scale and nominal level data for it, you know, so it's, you know, sometimes it's the best you can do, but it is definitely the lesser of the 2, right? You can get a lot more analysis out of ratio level data. There definitely is a hierarchy to data. Ratio level is the gold standard of data. And then as you come down, ordinal, you know, would be silver, nominal would be bronze, you know, it's kind of that kind of thing. And then you could also do regression analysis with frequency counts. You just don't do normal regression. You end up doing things like logistic regression and these other tools that you have to use when you have that kind of data. So that's, you know, and that all comes back to, you know, what kind of questions are you investigating, right? So you would do a different analysis depending on what you were trying to determine, right? If you're trying to see a difference between things, then you're going to do t-tests and ANOVAs and things like that, or chi-squares and those kind of things. If you're trying to see if things are related, then you're doing correlations, right? So it just depends on what you're investigating.
So this is all for quantitative. So let's say if our study is qualitative, then it will be research question rather than hypothesis.
Well, the only thing you can do with qualitative data is do like post hoc analysis, where you just kind of look at are there patterns and things like that. But with qualitative data, you can still do frequency counts, and with frequency counts, you can still do t-tests and chi-squares and hypothesis tests. You just have to make sure that you're wording your question correctly.
Got it. And you said you have it on your website?
Yeah, I've got a video on my website where I discuss different types of analyses. I'm trying to remember what it is.
So when we are done with this class, will we still have access to these videos if we bookmark them?
Oh yeah, my website's not, my YouTube channel is not going anywhere.
Okay.
I just want to make sure when I have to take the next 10-week stats course, I don't know if you teach that or not, but I'm going to try to get you for my section if you do.
I don't.
Damn it.
Yeah, they only have me teaching 807.
You make statistics relatable. I mean, I actually
know.
like statistics, but you actually make it very relatable. Your videos like just tell you the stuff that's like very academic that we're not going to use in application. And it's very helpful to think of it that way.
Yeah, I've always tried to gear it towards an adult audience that doesn't need to know all the minutia. That's why they pay me the big bucks. That's why I can't have, that's why I'm going out of town next week. I've got to go consult on a big project. So that's where I'll be. Yeah, it's gosh, I don't see it in this list. Where maybe it's under one of my other ones. I know I did it somewhere. But I did a thing where it compared different types of tests. But I can't think of where it is right now. If you just go on my way, I mean, if you just, if you just go on YouTube in general and just do, statistical analyses, you'll get videos, comparing statistical analyses, and you'll get videos that talk about the difference between, this and that and the other thing. But really, when you're talking about your dissertation, this is how you should be thinking about your dissertation. Number one, you need to identify a problem that needs to be solved. Because if you don't have a problem that needs to be solved, then your dissertation doesn't pass the so what test, because you don't want somebody to be able to read your dissertation and go, well, so what? You're not, why did I waste my time reading this thing? There needs to be a problem that you think you can solve. And then the second thing you do is, come up with a solution, or propose, that's a better word, propose a solution. This is what I think will fix this problem. And then now that you have a proposed solution, the next step is to design a study to test said solution. And so that's where you come up with your research questions. You come up with the data that you need. You come up with how to collect it. And then you come up with how to analyze it. Then what do? You collect and analyze. All right. And then after you analyze it, you summarize it. Summarize. And those are basically your chapters, right? Chapter 1 is identify the problem. Chapter 2, your lit review, is where you check to make sure somebody else hasn't already solved it the way you want to solve it. Chapter 3, your methodologies chapter, that's where you discuss all of this. You talk about your research questions, you talk about the data that you're going to need, how you're going to collect your data, how you're going to analyze it. Chapter 5 is your results chapter, where you do all of this and summarize it. And that's your dissertation.
So, Dr. McBride, what's really funny is that this class needs to be farther up in the regimen, or in the number of in the course selection process, because if someone explained this right, just what you just explained,
yeah,
in semester 1 or in the first 2-3 courses, all of this would have looked totally different for me.
Yeah, I know. Yeah, well, what they don't need to move my class up. What they need is they just need a class early on that describes how to write a dissertation. That's the problem. This is a very simple set of 5 steps. This is how every dissertation should go. This is the thought process on, this is basically how every scientist decides to do something, right? You identify a problem, you propose a solution, you design a study to test that solution, then you go through the steps of testing it, you look back at your solution, and you summarize whether or not it worked. That's really just research. That's how you do any kind of research. And a dissertation is basically just a lot of flowery words written around that research. And so, yeah, they should, graduate studies programs need to give students just a basic course on research design early on in their track. I agree, because really, as a doctoral student, you should be thinking about this on day 1. Far too often, students take way too long until they start thinking about what they're going to do their dissertation on. You should have an idea of what your dissertation is the day you go into grad school, because every damn thing you learn in grad school should be focused on your dissertation, because every topic you learn will somehow apply to your dissertation. So if you already have that dissertation idea, doesn't have to be completely fleshed out, but just that spark of an idea, then every time you learn something, you can start thinking about, well, how does that work in context of my question? Oh, yeah. Then that does this, and then I do this. And it just, it keeps things focused, and you're not learning stuff and going, why the hell am I learning this, right? It makes everything make a lot more sense.
But even the way you've explained how the data is used and how we're going to use this statistical analysis, I mean, it makes more sense.
Yeah.
And that's why I say if some of this information is pushed farther up into the course, then I would like to say 2 semesters ago, I had a course that had I understood what I'm understanding now, then I would have addressed some things in regards to my research and then my problem a little bit differently.
Yeah. I agree with you, Anthony, that this topic, just these simple 5 steps, needs to be addressed much earlier in most programs. Absolutely. And hopefully, if you need to readjust some things, it's not going to be too big of a problem to do so. But, as far as you guys are asking, once you're out of my class, the Google Drive never changes. It's been there for 7 years, I think now. And the link has always been there. So you'll always have access to everything in the Google Drive. You'll have access to the SAS how-to. You'll have access to all of the recordings of all the meet sessions if you want to go back and watch any of those. You'll always have access to all my videos, either through the links in that or just going straight to my YouTube channel. And you'll always have access to me. You can always send me an email. I just got an email just the other day from an ex-student who's working on her dissertation. And she wants to hire me to help do some of her analyses. And I'm more than happy to always work as a consultant for people. I'm more than happy to give free advice. If you have questions, I will always just answer your questions. But she wants me to actually do some in-depth, help her develop her questions, help her develop her research, and how she's going to collect things, basically design her study from the ground up. And so I do that for a fee. And that, like I said, that's what I'm doing tomorrow. I'm consulting for a very large company where they pay me way more than I would ever charge you guys, but I'm happy to do it for you guys for peanuts. So you always got my information if you need help.
That's good to know. Thank you.
Yeah. But unfortunately, I don't teach 810, but I hear good things about most.
I wish that you did. And I agree too. I think seeing it framed up this way, I mean, like I matriculated through this like in the life sciences, but like I said, you make the statistics like very digestible for someone that then has to translate this into, and I'm leaning towards a mixed methods dissertation approach.
Sure.
But I will definitely be, I will more than gladly pay, because what I will tell you is the folks at my job that are statisticians, data scientists, and methodologists, they are completely undervalued.
Yeah.
Because that is a discipline all in of itself.
It is, absolutely. Yeah, it is, absolutely. Well, any other questions about the homework for this week or anything before we go?
Can I ask just one question, and it's more related to the final project?
Sure.
And this has to do with my questions, like, again, probably me getting confused between binomial distribution and normal distributions.
Yep.
But it looks like in one of those problems, they're taking like a random sample. And maybe I'm wrong. And I'm just trying to, like, I know, as it's question 4 on the part 1.
Question 4.
It's asking, I mean, I think what they're trying to determine is like whether or not the sample that's selected from this, historical log is representative. Yeah.
All right. This one is an extremely complex question. I honestly don't know why they have it on the final, other than to, I guess, really piss people off or really challenge them. But I'll tell you this, it's a multi-step process, right? So the first thing we have to do is we have to just figure out the probability of a family purchasing more than 4 freights. And that's really easy because all you got to do is add the probabilities for 5 freights and 6 freights from the data, right? So they have the data that comes along with this. There's a data table and it lists the probability that a family purchased 5 freights and the probability that a family bought 6 freights. You add those 2 numbers together. That now gives you the probability that any random family, from this data set would buy more than 4 freights. So now you've got that. Okay, so now that we have that probability, now we can run a simple binomial CDF with a sample size of 6 and the probability that we just calculated, and then the number of successes being 4. Because in this question, right, it says this list includes information for 6 families. Of these 6 families, 5 families purchased more than 4 freights. So using the information contained in calculate the probability that at least 5 of 6 German immigrant families purchased more than 4 freights. So our success is purchasing more than 4 freights, right? So that's where we add the 5 and the 6 together and we get a probability of that. Let's just say it's 7%. So our probability of success is 7%. We have a sample size of 6, and we want to know what's the probability that 5 families, right? 5 families, let's see, what's calculate the probability that at least 5 of them purchased these 4 freights. So at least 5 of them had a success. Well, we can't do at least questions with CDFs. Remember, CDFs do something and less than. So we would do a binomial CDF of 4 with our probability of success of being 7%, right? So we basically would have our sample size would be 6. Our probability would be, let's say, 7%. We would set X to be 4, and we would do a binomial CDF of 4. And that basically gives us the probability of 0, 1, 2, 3, or 4 families, having a success, i.e. purchasing more than 4 freights. And then we would do 1 minus that to get the other part, to get the 5 and 6. And that's how you would calculate this one. So like I said, it's a multi-step process. The first thing is you have to calculate the P. You have to figure out what the P is, and that's really easy. We add our probabilities from our data. And then we do 1 minus the CDF of 4, because that will give us the probability of 5 or more of them buying, these numbers of freights. And then when we get that probability, the idea is to say, well, then does it seem like this set of data came from the new Walt, came from the same set of data? Well, if the probability is really, really big, then yeah, it came from the same data set. But if the probability is really, really small, then no, it's not likely, right? Because the idea is if it was from the same data set, then the probability of this happening shouldn't be super, super small. And so if it is super, super small, then you have to go, oh, well, then this data probably came from something other than the new Welt stuff. But if the probability was big, then you go, oh yeah, then, or on par with what it would have been in the other set of data, then you go, oh yeah, then we're pretty good. So that's how you do that one. It's a tough one.
Okay. What I couldn't understand, I knew it was a distribution. I knew I needed a probability, but what I was getting tripped up on was, I thought it was a binomial, but that's again where I get hung up on needing to set that X lower because you're making that adjustment.
Right. Yeah. No, it's a binomial, and you just set X to be 4, and then you got to calculate the probability of the 5s and 6 freights from the data set, and then 1 minus that, and you're good to go. Anything else?
Not for me, Doc. I'm gonna call it a night. Hey, man, be safe with your travels, and good
Thanks,
luck
man.
on your consulting work.
Thanks, man. We'll see you next week.
All right. Well, no, you won't see us next week, right?
No, I sent a second email out. I was wrong with my dates. I can actually still make it next. Let me double check.
You
Yeah,
said Thursday.
next Thursday, the 9th is still fine, because I fly home on the 8th and then I fly back out on the 10th. So I'll be home on the 9th. So we'll be able to meet. We'll meet on the 9th where I can answer all of your final questions. You'll just have to deal with, watching the videos for as far as the week 5 lecture material is concerned.
Okay, so it's no Monday class, but Thursday class.
You got it.
Okay, good deal. Glad we cleared that up.
Yep.
And that
Thanks
will
a
be our
lot.
last
Hey,
class.
good night, everybody.
Good night, Anthony. What was that, Vandana?
So that will be our last class. So we will not have any class following week for the final project. If
Correct.
we have any question, that will be just via email.
Yeah, unless a lot of people say that they really want to meet, then we'll try and figure out a time that we can meet on the 17th. But that's my only available time on that last week is the 17th, which is a Friday. So I'm hoping everybody is fine. I've always taught this course without any meetings on the last week because we don't have any new material, and everybody asks all the questions that they need on the week 5, and then it's kind of like push the little birds out of the nest and let them fly, and go off and do your final project kind of thing, and then ask questions via email or submit them to the discussion board.
Okay, sounds good.
Yep.
Okay, thank you.
Of course.
Thank you very much.
Yep. Good night,
Safe
everybody.
travels to you. Thank
Thank
you.
you.
Good night.
Good night.